So how can we improve our Hartree-Fock? Well, we do the wave function way, and that means we improve the wave function. How to improve on Hartree-Fock. So our wave function is now not just a single Hartree-Fock determinant, but as we saw with the simple example for H2, which is behind the green board, we add some other determinants as well. And in general, we add a lot of them. And then in the dissociation limit, it was sort of 1-to-1. But here we have some expansion coefficients. And the whole business about the correlated wave function methods is to find those coefficients. And we can either write it in this way that we say, okay, we have the Hartree-Fock, and then we have corrections to it. Or we could also just say, okay, and use different index here. We throw them all together. We have a linear combination of Slater determinants, and we have to find the coefficients in which way to combine them, and there are different methods, different ways of doing that. And those phi j, those are the Slater determinants, like the ones for hydrogen in a minimal basis set. There were 6. So they actually form a basis, like your basis functions, CCP set, but this is now a many electron basis set. So therefore, because we have these determinants as being a basis set, many electron basis set, many electron wave function basis set, we sometimes call the other basis set also one electron basis functions in order to distinguish. Do we talk about the Slater determinants in a multi-configurational approach, or do we talk about the basis functions, one electron basis functions? Now for the hydrogen, in the minimal basis set we had those 6. This was a sum over 6. But if you now go away from the minimal basis set, in the hydrogen we get more molecular orbitals, we have more basis functions, and therefore we get more molecular orbitals instead of the 2. We still have only 1 occupied, and then several more which are unoccupied. And that means we will have many more singly excited and many more doubly excited determinants. But for hydrogen with 2 electrons, we still only have singly doubly excited determinants. There are only 2 electrons. If you go away from a 2-electron system to a many electron system, then we will get not only singly and doubly excited determinants, but we will get also other kind of determinants. And so we have a basis set of Slater determinants. And if you write it up like this, then in a way, never mind how they look like, we just have this set of basis functions. If you write it like here, where we single out one, the Hartree-Fock Slater determinant, then it makes sense to try to put some order in all the other determinants which we can make from the molecular orbitals. So basically we can make all those determinants by choosing as many molecular orbitals as we need for the electrons, and then we have a large number of possibilities. And the normal way is then that one sort of really tries to keep an order of them, assort them by relating them to the Hartree-Fock. So we have sort of this set of base function, we have the Hartree-Fock determinant, and then we get a class of determinants which we call the single excited determinants, which are made in the way that you take one of the occupied orbitals, for example I, and you replace it by one of the virtual orbitals. And you will see very much nowadays in the literature, and I think also in Frank's book, the notation is that you call occupied orbitals, that's right here, I, J, K, L, I guess also M and N, those are typically occupied orbitals. And A, B, C, D are unoccupied or virtual orbitals. Unoccupied or virtual. And when you see an equation where you have P and Q and R and S, then it can be both. So that's some of the sort of hidden notations which you better be sort of aware of, otherwise it's difficult to read what that means. That means you have replaced one occupied orbital, and that's later determined, with one of the unoccupied orbitals, one of the virtual orbitals. And the orbitals which are occupied, those are the ones which are used here. So it only makes sense to talk about occupied and unoccupied orbitals if you have defined what your Hartree-Fock wave function is, determinant is. And then of course you can have the double excited ones, like we had the single one for the hydrogen, which then would be like this. You have replaced two of the occupied orbitals with two virtual ones. You can have triple excited, quadruple excited up to, I mean, as many electrons there are in the system. And they get, in each of those subclasses, you get more and more. It sort of explodes. Now, they are called single, double, triple excited determinants. But I think in general this is actually a really bad word for it, because it generates an association which shouldn't be there, at least not always. Because very much get the idea this has something to do with excited states in here. That's not the case. Yes, eventually when we talk about excited states and calculation of excitation energies, we will use those again as basis functions for describing the excited state. But it would be much better, but of course we can't roll time back to call them singly replaced and doubly replaced determinants and triply replaced determinants. Because this is just a way to classify, to keep some order of which determinants we have. In a way, this is just a different electron configuration. Or a different way of making functions. If you have a complete set of orbitals, we can make a complete set of many electron wave function determinants, which we then can use to express any kind of function which has the same boundary conditions. So please don't always associate this with sort of an excited state. Now it's the other way around. We can use those for describing excited states approximately. This is just another determinant.